Hello, everyone. Today I'll be talking about Kirchhoff's voltage law, or KVL, in AC circuits. KVL is one of the most important principles used to analyze electrical circuits. While it is usually introduced with DC circuits, it also plays a major role in AC circuit analysis. In this presentation, I'll briefly explain what KVL is, what AC circuits are, why applying KVL is slightly different in AC systems, and then I'll go through a few worked examples. First, we'll start with the basic idea of Kirchhoff's voltage law. Then we'll review AC circuits and their characteristics. After that, we'll discuss why KVL behaves differently in AC circuits, mainly because of impedance and phase angles. Next, we'll go through 3 examples showing how KVL is applied in RL, RC, and RLC circuits. Finally, we'll look at some real-world applications where KVL is used in electrical engineering. Kirchhoff's voltage law states that the sum of all voltages around a closed loop in a circuit equals 0. This law is based on the conservation of energy. In simple terms, the energy supplied by a source must equal the energy used by the components in the loop. Mathematically, we write it as sigma vi equals 0. For example, if a source provides voltage to a loop with several components, the total voltage drops across those components must equal the source voltage. Now, let's talk about AC circuits. AC stands for alternating current, which means the voltage and current change direction periodically instead of flowing in only one direction like DC. AC signals usually follow a sinusoidal waveform. Typical AC circuits include components like resistors, capacitors, and inductors, each of which affects voltage and current differently. In AC circuits, applying KVL becomes slightly more complex. Instead of simple resistance, we work with impedance, which combines resistance and reactance. Impedance is written as Z equals R plus JX. Another key difference is phase shift. For example, in an inductor, the voltage leads the current by 90 degrees, while in a capacitor, the voltage lags the current. Because of this, we usually use phasor analysis when applying KVL in AC circuits. Let's look at the first example, which is an RL series circuit. First, we calculate the inductive reactance using the formula. XL equals 2PFL. Once we find the reactance, we determine the total impedance, which includes both resistance and inductive reactance. Next, we calculate the current using Ohm's law for AC circuits, which is voltage divided by impedance. Finally, we calculate the voltage across the resistor and the inductor and verify that source voltage equals the sum of the voltage drops. This confirms that KVL is satisfied. Notice that the current lags the voltage because inductive reactance introduces a positive phase angle. In this second example, we analyze an RC circuit. First, we calculate the capacitive reactance using XC equals 1 over 2 PIFC. Then we determine the total impedance of the circuit. After that, we calculate the current and the voltage drops across the resistor and capacitor. When we add the voltages using phasor addition, we again see that they equal the source voltage, which verifies Kirchhoff's voltage law. In this case, the current leads the voltage, which is a characteristic behavior of capacitive circuits. Finally, we look at an RLC circuit, which includes resistance, inductance, and capacitance. First, we calculate both inductive and capacitive reactances. Then we determine the net reactance and total impedance. Using this impedance, we calculate the circuit current and then the voltage across each component. When we add all the voltages together, the result equals the source voltage, again confirming KVL in AC circuits. In this example, we can also observe how the circuit behavior depends on whether inductive or capacitive reactance dominates. KVL is widely used in many areas of electrical engineering. For example, it is used in power systems to analyze voltage distribution across transmission lines. It is also important in electronic circuit design, helping engineers design reliable circuits. Additionally, KVL is used in signal processing and communication systems when analyzing filters, amplifiers, and RF circuits. Overall, KVL is one of the fundamental tools engineers use to understand and design electrical systems.